Welcome to Civil Engineering Edge, where we dive deep into the world of civil engineering concepts that shape our built environment. In today's video, we'll explore the science of geotechnical engineering, a field that studies soil, rocks, and their behavior under different conditions. From laboratory testing to field investigations and computer simulations, geotechnical engineering provides the foundation for safe and sustainable structures. Stay tuned as we unlock the hidden secrets beneath our feet that make modern construction possible. The Science of Geotechnical Engineering. Introduction. Geotechnical engineering is a core branch of civil engineering that deals with the behavior of earth materials, primarily soil and rock. Every structure, whether it's a skyscraper, dam, tunnel, or bridge, ultimately relies on the stability of the ground it rests upon. Understanding soil properties is crucial because, unlike steel or concrete, soil is a natural and highly variable material. Its composition, density, moisture content, and shear strength can vary dramatically, even within short distances. Geotechnical engineers study these variations to design foundations and earth-retaining structures that can safely support loads. They analyze how soil interacts with water, how it responds to stress, and how it behaves during events like earthquakes or heavy rainfall. This makes geotechnical engineering a blend of geology, physics, and engineering principles. By investigating subsurface conditions, engineers can predict settlement, slope stability, and bearing capacity. They also design preventive measures against soil failures such as landslides or liquefaction. Simply put, geotechnical engineering ensures that structures are built on reliable foundations. Without this discipline, the world of construction would face constant risks of instability. In the sections ahead, we'll uncover how testing, analysis, and simulations help geotechnical engineers bring science into real-world practice. Testing and analysis, unlocking the secrets of soil. 250 words. The ground beneath us may seem solid, but to an engineer, it's full of mysteries. Soil is not a uniform material. It can contain layers of sand, clay, silt, gravel, or even organic matter, each behaving differently under pressure. To design safe foundations, geotechnical engineers must unlock these secrets through systematic testing and analysis. Soil testing begins into major environments, the field and the laboratory. In the field, engineers perform tests such as the standard penetration test, SPT, or cone penetration test, CPT, to measure soil strength and density directly in place. Samples are then taken to the laboratory, where they undergo detailed examinations for grain size distribution, Atterberg limits, permeability, compaction, and shear strength. These results reveal the soil's ability to support loads and resist deformation, but testing alone isn't enough. The collected data must be analyzed carefully to predict how soil will perform under real-world conditions. For example, sandy soils may drain water quickly but lack cohesion, while clays may swell, shrink, or soften when wet. This understanding helps engineers design foundations that resist settlement and failures. Ultimately, testing and analysis form the foundation of every geotechnical project. By decoding soil behavior, engineers transform uncertainties into reliable design parameters, ensuring safe, efficient, and sustainable construction. Geotechnical testing, the laboratory and field method. Geotechnical testing combines field investigations with laboratory experiments to provide a comprehensive picture of subsurface conditions. Each method reveals a unique aspect of soil performance. Field methods are essential for in situ evaluation. The standard penetration test, SPT, involves driving a sampler into the ground to measure resistance, which indicates soil density and strength. The cone penetration test, CPT, pushes a cone into the soil, continuously recording resistance, giving detailed soil stratification. Other techniques include plate load tests for bearing capacity and vein shear tests for soft clays. Field testing offers real-time insights into soil conditions without disturbing its natural state. Laboratory testing takes collected samples and examines their fundamental properties. Grain size analysis classifies soil into sand, silt, and clay fractions. Atterberg limits define the plasticity and shrink swell potential of fine soils. Permeability tests measure water flow through soil, while consolidation tests predict settlement over time. Shear box and triaxial tests simulate real stress conditions to evaluate soil strength. Together, these tests create a reliable database of soil behavior. While field methods give rapid results in natural conditions, laboratory tests provide precise and controlled measurements. Engineers combine both to design stable foundations, retaining walls, embankments, and pavements. Without these investigations, construction projects would face uncertainties and risks. Testing ensures that every structure stands on a foundation that has been scientifically evaluated, minimizing the chances of unexpected failures. Analyzing soil data. Interpreting the results, collecting soil data is only the first step. The real challenge lies in interpreting the results. Soil properties are not absolute, they vary across sites, depths, and even seasons. Engineers must transform raw data into meaningful conclusions that guide design decisions. For example, standard penetration test SPT values must be corrected for overburden pressure and hammer efficiency to reflect true soil strength. Laboratory results, such as plasticity index or permeability, must be compared with classification systems like the Unified Soil Classification System USCS or Indian Standard Codes. Engineers then determine key parameters: cohesion, angle of internal friction, and modulus of elasticity that describe soil behavior mathematically. One crucial aspect of analysis is assessing bearing capacity, the soil's ability to support structural loads. By combining test results with theoretical equations and empirical correlations, engineers estimate safe load limits. Another important factor is settlement prediction, evaluating how much a foundation will sink over time due to soil compression. Similarly, slope stability analysis helps assess risks of landslides or embankment failures. Data interpretation also involves risk assessment. Engineers must account for variability and uncertainties by applying safety factors. This ensures designs remain stable even under unexpected conditions such as heavy rainfall, seismic activity, or fluctuating groundwater levels. Ultimately, interpreting soil data transforms scattered numbers into a blueprint for construction safety. By connecting laboratory precision with real-world performance, geotechnical engineers provide the reliable groundwork on which our modern infrastructure stands. Computer simulations modeling soil behavior under load. In today's digital era, computer simulations have become an indispensable tool in geotechnical engineering. While testing and analysis provide valuable data, computer models allow engineers to visualize and predict soil behavior under complex loading conditions that would be difficult to replicate physically. Finite element method FEM software, such as Plaxis or Geo5, enables engineers to create virtual soil models that simulate stress, strain, and displacement under different loads. For example, simulations can predict how a foundation will settle when subjected to heavy building loads, how a tunnel will affect surrounding soil, or how an embankment slope will behave during rainfall. One key advantage of simulations is their ability to account for non-linear and time-dependent soil behavior. Soils exhibit unique characteristics: plastic deformation, consolidation, and creep that evolve with time. By modeling these effects, engineers can foresee long-term performance and design accordingly. Simulations also enhance safety and cost efficiency. Instead of relying solely on conservative estimates, engineers can optimize designs by testing different scenarios virtually, reducing unnecessary construction costs while maintaining safety margins. Additionally, simulations are vital for assessing extreme events like earthquakes or floods, helping in disaster-resilient design. By integrating soil testing results with advanced computer modeling, geotechnical engineers gain a powerful decision-making tool. These virtual experiments bridge the gap between theory and practice, ensuring that every structure is not only stable today, but remains safe for decades to come. Geotechnical engineering may often go unnoticed, but it is the silent force behind every successful construction project. From testing soil in the lab and field to interpreting data and running computer simulations, this science ensures that our structures stand strong and secure. By understanding the ground beneath us, engineers build the foundation of modern civilization. Thank you for watching Civil Engineering Edge. Don't forget to like, share, and subscribe for more in-depth insights into the world of civil engineering.